All right, welcome to This Explainer. Today, we are literally cracking open the engines of modern databases to see exactly how they store and retrieve our data. I mean, we all use applications every single day that seamlessly save our info and fetch it back in milliseconds. But what is actually happening on the disk when you hit save? Today, we're going to peer right under the hood and decode the engineering decisions that make massive scale possible.
We've got a fascinating journey ahead, so here's our roadmap for navigating all this. We are hitting 1. The two database worlds. 2. Appending logs, LSM trees. 3. Updating in place, B trees. 4. The storage engine debate. 5. Secondary and in-memory indexes. And finally, 6. Analytics and advanced indexing. Let's jump right in.
Section 1. The two database worlds. To make sense of everything we're about to cover, we first need to divide the database universe right down the middle based on how the data is actually used. This divide is absolutely crucial. On one side, we have OLTP, or Online Transaction Processing. This is all about rapidly processing your users' everyday transactions. Think of things like looking up a user's profile, inserting a new comment, or checking out a shopping cart. It involves finding individual records super quickly. But on the flip side is OLAP, Online Analytical Processing. This is a totally different beast. This is where business analysts crunch massive historical data sets to find trends, like, say, aggregating the sales of every single product across hundreds of stores over 5 years. Because these workloads are so vastly different, the engines that power them look completely different under the hood.
Which brings us to Section 2, Appending Logs, LSM trees. Let's zoom in on the operational side, that OLTP world, starting with a storage engine that relies on a surprisingly simple yet incredibly powerful idea: just keep appending data.
The core philosophy here is that the absolute fastest way to write data is to simply append it to the end of a file. But we also need to be able to find it again efficiently. So, when you write to a log-structured engine, the data first hits something called a memtable. You can think of the memtable as a fast, highly organized waiting room sitting right there in memory, often built using a red-black tree or a skip list. It buffers those incoming writes, sorting them by their key so they're perfectly primed to be written to the disk in a highly organized way.
Now, when that in-memory memtable gets full, it gets saved to the disk as an immutable file called an SS table, or sorted string table. Over time, you're going to end up with lots of these SS table files. To prevent your read queries from getting painfully slow, a background process called compaction constantly merges these files together. It's basically cleaning house, keeping the newest value for a key, tossing out the older overwritten values, and dropping any data that has a tombstone, which is just a special marker telling the system a record was deleted. And that right there is the heart of the log-structured merge tree, or LSM tree.
But there is a catch. Because data is spread across multiple SC stable segments, looking for a specific piece of data, especially data that doesn't actually exist in your database, could force the engine to check every single file. That is incredibly slow. To fix this, these engines use Bloom filters. It's a clever mathematical trick using bit arrays and hash functions that allows the database to quickly say, nope, your data is definitely not in this file. If the Bloom filter says no, the database saves a time-consuming trip to the disk.
Okay, but what if we don't want to continually append data and merge files in the background? Enter Section 3, Updating in Place, B trees. What if we just want to update the data right where it lives on the disk?
To build a predictable search path, the B tree takes a totally different philosophical approach. Instead of appending logs, it breaks the database down into fixed-size blocks, or pages, traditionally about 4 kilobytes in size. It forms a tree structure. When you search for a key, you start at the root page, and you follow the range boundaries down through the child pages until you hit the exact leaf page where your data lives. Because the tree stays perfectly balanced, you literally only need to follow 3 or 4 page references to find any record in a massive database. It's amazing.
However, overwriting a page directly on disk is risky. Imagine the database is halfway through updating a leaf page and the server loses power. Your data would be totally corrupted. So, B trees rely on a write-ahead log, or WAL. This is an append-only file that serves as a crash recovery safety net. Every single modification must be written to this log before the database is allowed to actually overwrite the B tree pages. If the system crashes, no big deal. The database simply replays the log to restore itself to a consistent state.
Section 4, The storage engine debate. The crucial point here is choosing between these two titans, LSM trees and B trees, and that choice is based entirely on the engineering trade-offs of your specific application. Before we compare them head-to-head, you really have to understand a concept called write amplification. This is the ratio of bytes actually written to the physical disk compared to the logical bytes your application asked to write.
In an LSM tree, data is written to the log, then the mem table, flushed to disk, and then repeatedly rewritten during compaction. In a B tree, data is written to the WAL, and then whole pages might be written out just to change a few bytes. If your app writes too much data, an engine with high write amplification will literally wear out and burn through your solid-state drives.
When comparing the two, it really comes down to throughput. If your app has an absolute avalanche of incoming writes, like a system recording sensor data every second, LSM trees are your best friend. They turn random writes into sequential writes, which hardware loves, handling massive throughput. But if you need highly predictable and blazing fast read queries without the unpredictable overhead of background compaction eating up your disk bandwidth, the classic B tree is usually your winner.
Finding data by its primary key is just the baseline, though. Real applications need to search by user IDs, email addresses, or product colors. So let's hit Section 5, Secondary and In-Memory Indexes, and explore how we search for everything else.
Depending on how fast you need your results, a secondary index handles the actual data in one of a few ways. It can use a heap file approach, where the index just stores a pointer to the location of the full record somewhere else on disk. Alternatively, a clustered index stores the actual complete row data directly within the index structure itself to save you a trip. And a nice middle ground is the covering index, which just duplicates a few frequently queried columns right inside the index to speed up those specific read requests.
Now, what happens if your database is too huge to fit on one machine and is sharded across multiple servers? If you use local secondary indexes, like say searching for a red car, the index is tied to the local shard. Because you don't know which shard holds the red cars, you are forced to send your query to every single shard, ask them all for their red cars, and combine the results. This scatter-gather approach can be pretty expensive.
While we're talking about speed, I have a quick myth-buster for you regarding in-memory databases. People often assume these databases are wildly fast simply because reading from RAM is faster than reading from a disk. But honestly, modern operating systems heavily cache disk blocks in RAM anyway. The real reason in-memory databases absolutely fly is that they entirely skip the grueling CPU work of formatting and encoding data structures to be safe for a hard drive. They just avoid the translation step entirely.
Let's completely shift gears now and leave the operational OLTP world behind. Section 6. Analytics and Advanced Indexing.
Think about this. What if you were tasked with a business intelligence query? Say, calculating the average net price of a specific product sold over the last 10 years across a petabyte of data. A standard row-oriented B tree will grind to an absolute halt. It would have to drag entire rows into memory, with all their 100 columns, just to read the 2 columns you actually care about. The elegant solution to this massive bottleneck is column-oriented storage. Instead of storing all the values for one row together, analytical databases flip the layout sideways. They store all the values from a single column together in one file. This means if your query only needs the date and net price columns, it only loads those specific files from disk. Plus, because a column contains a lot of the exact same type of data in a row, it compresses beautifully, saving a staggering amount of disk I/O.
And the performance gains don't stop at the disk. By keeping data in these dense, compressed columns, analytical query engines can use something called vectorized query execution. Instead of evaluating one clunky row at a time, the CPU can churn through arrays of millions of records in tight, highly optimized loops that fit perfectly inside the processor's fast cache. It is a masterclass in hardware efficiency.
Finally, it's worth noting that these foundational storage concepts extend to the absolute cutting edge. Full-text search engines use inverted indexes to let you find words within documents. Geospatial databases use multidimensional indexes to let you search within a map's bounding box. And modern AI relies on high-dimensional vector embeddings, using specialized indexes like HNSW to find data that is semantically similar rather than just looking for exact keyword matches.
We've seen it all today, from the append-only logs of LSM trees to the careful in-place updates of B trees to the sideways logic of columnar analytics. Every single design decision favors one type of workload at the expense of another. There is absolutely no such thing as a perfect database, only the right set of trade-offs. So I leave you with this. Look at the architecture you rely on every day and ask yourself, knowing what's happening under the hood, are you entirely sure you're using the right tool for the job? Thanks for exploring the depths of data storage with me in this explainer. Keep asking questions, and I'll catch you next time.